On July 30th, 2026, IBM did something no major quantum computing company had ever attempted before. It didn't make one quantum advantage announcement. It made three on the exact same day, each one independently verified, each one submitted publicly for the entire research community to try to tear apart. For years, quantum computing has been plagued by big, bold claims that quietly fell apart under scrutiny. IBM just tried something radically different, claiming victory and simultaneously inviting the world to prove it wrong in real time. And buried inside that announcement is a genuinely uncomfortable question for Microsoft, a company that just spent the last several months defending its own quantum claims against exactly the kind of scrutiny IBM is now actively inviting. Let's start with what actually happened, because the scale of this coordinated announcement is genuinely unusual for the industry. IBM rolled out three separate quantum advantage demonstrations simultaneously. The first, developed alongside Japan's Riken Center for Computational Science, used a 77-qubit IBM Heron processor working directly alongside all 152,064 nodes of Fugaku, one of the most powerful supercomputers on Earth, to calculate the electronic structure of iron-sulfur clusters, a genuinely difficult problem in quantum chemistry with real relevance to biology and materials science. The second, developed with the University of Chicago, demonstrated quantum advantage using logical circuits, meaning error-corrected, encoded quantum circuits verified to perform computations beyond what leading classical simulation methods could match, representing one of the largest demonstrations of logical quantum computing achieved anywhere to date. The third, developed with a Finland-founded quantum software company called Algorithmike, simulated a genuinely complex quantum material, a simulation that had already been running publicly on IBM's own quantum advantage tracker for 8 straight months without a single classical method successfully matching its results across the full problem regime being studied. That last detail is worth sitting with for a moment, because it points directly at the most important, most genuinely novel part of this entire announcement. IBM didn't just claim quantum advantage and move on. Rather than declaring victory once and hoping nobody looks too closely, IBM structured this announcement as an open, standing invitation for the entire scientific community to keep trying to break it. To understand why that specific approach matters so much right now, you have to understand the credibility crisis quantum computing has been quietly wrestling with for years. IBM's own CEO, Arvind Krishna, predicted back in April 2026 that the company's partners would achieve the first genuine examples of quantum advantage sometime that same year, leveraging IBM's hardware. That's a bold, specific public prediction from the head of one of the most established names in the entire industry. But IBM has also been candid, almost unusually candid, about how messy and contested this specific corner of computer science genuinely is. At CES earlier in 2026, IBM's own quantum lead, Borja Perpadre, openly admitted that just days before presenting certain results, his own team had discovered a classical method that actually outperformed their quantum computer on the exact same problem, describing this constant back and forth as simply the nature of science, a feedback loop where quantum tries to outperform classical tries to catch back up over and over again. That kind of honesty matters enormously in an industry that has for years struggled with the gap between confident public announcements and results that actually hold up once independent researchers get a chance to examine them closely. IBM's own definition of quantum advantage, achieving results that are cheaper, faster, or more accurate than classical computation alone, is notably broader and more practically grounded than the stricter academic gold standard, sometimes called quantum supremacy, solving a problem no classical computer could ever solve at all, regardless of cost or time. Some critics have pointed out that this broader, more commercially focused definition makes IBM's claims somewhat easier to achieve than the field's most demanding theoretical bar. IBM's response to that exact criticism is precisely the quantum advantage tracker itself, a mechanism specifically designed to let skeptics test that claim themselves, rather than simply asking the public to take IBM's word for it. This is exactly where Microsoft's situation becomes genuinely uncomfortable, and it's worth being precise about why. Just weeks before IBM's triple announcement, the journal Nature published a formal peer-reviewed critique directly challenging the foundational research behind Microsoft's Majorana 1 quantum chip. Physicist Henry Legg argued that Microsoft's own detection software had selectively emphasized favorable-looking data while omitting other results generated using the exact same methodology that told a considerably less conclusive story. Microsoft was granted a formal right of reply in the same issue, defending its research, but the underlying dispute remains genuinely unresolved, with independent physicists outside Microsoft continuing to express real skepticism about whether the company's core claims about Majorana zero modes actually hold up under close, rigorous examination. Now place that ongoing controversy directly alongside IBM's brand new approach, not just claiming quantum advantage, but building an entire public infrastructure specifically inviting continuous, open challenge from the broader scientific community. The contrast is stark, and it's not a flattering one for Microsoft. Where Microsoft's foundational quantum claims are currently being contested after the fact through a formal academic dispute playing out in the pages of a major journal, IBM has essentially gotten ahead of that exact same dynamic, building the challenge mechanism directly into its own announcement from day one. IBM isn't waiting for outside physicists to eventually discover potential problems with its data years down the line. It's actively inviting that scrutiny immediately, treating the strength of its claims as something that should be continuously tested, rather than something the company simply asserts and hopes goes unquestioned. That difference in approach might end up mattering more for the broader industry's future than the specific technical details of either company's underlying hardware. Quantum computing has spent years accumulating a credibility problem, precisely because companies have historically been more eager to announce impressive-sounding milestones than to build durable, transparent mechanisms for verifying those milestones actually hold up. IBM's Quantum Advantage Tracker and Algorithm Q's parallel decision to publicly release its own best classical simulation methods, specifically so other researchers can stress test IBM's claims themselves, represents a genuinely different philosophy, one that treats scientific credibility as something actively built and continuously defended, rather than something simply declared in a press release and left unexamined. To really appreciate why building a public challenge mechanism like the Quantum Advantage Tracker represents such a meaningful shift, it helps to understand the specific, thorny scientific problem it's actually trying to solve. When a quantum computer produces a result for a genuinely difficult, large-scale problem, one of the central challenges researchers face is verification. If a classical computer could easily check whether the quantum computer's answer is correct, that would usually mean the problem wasn't actually beyond classical reach in the first place, undermining the entire claim of quantum advantage. But if no classical method can verify the answer at all, how can anyone, including the researchers who ran the experiment themselves, be confident the quantum computer's result is actually correct, rather than simply the product of accumulated hardware noise, calibration drift, or some other subtle experimental error masquerading as a genuine computational result? This verification problem has haunted quantum computing's most ambitious claims for years, stretching all the way back to Google's original 2019 quantum supremacy announcement, which drew immediate, extensive scrutiny from researchers, questioning whether classical methods might eventually catch up and match results that were initially declared impossible to replicate classically. In some well-documented cases across the broader field, exactly that has happened, with improved classical algorithms later managing to match or approach results that had originally been presented as clear evidence of quantum advantage, forcing companies to walk back or meaningfully qualify their original, more sweeping claims. IBM and Algorithm Q's approach directly targets this exact vulnerability. Rather than declaring victory and hoping no better classical method ever emerges, their framework involves actively stress testing the quantum results themselves, deliberately injecting controlled noise into the quantum devices, altering calibrations, and running the same circuits across multiple different IBM quantum processors, specifically checking whether the resulting computations remain stable and consistent despite these deliberate variations. According to the companies, achieving consistent results even under these intentionally challenging conditions provides meaningful evidence that the underlying quantum computation is producing genuinely stable, trustworthy solutions, rather than results that happen to look convincing under one narrow, carefully controlled set of experimental conditions, but would fall apart under any kind of closer, more adversarial examination. That kind of deliberately adversarial, self-skeptical testing methodology represents a meaningful maturation for an entire field that has, for years, been more focused on generating exciting headlines than on building the kind of rigorous, self-correcting verification infrastructure that more established scientific disciplines have relied on for decades. Algorithm Q's decision to simultaneously release its own best classical simulation methods to the wider research community, specifically so outside groups can use those exact same tools to try to challenge IBM's claims, extends that same philosophy even further, essentially handing potential critics the sharpest available tools and inviting them to use those tools aggressively, rather than hoping nobody ever develops sufficiently powerful classical methods to properly test the claim in the first place. It's worth pausing to consider how unusual this kind of radical, proactive transparency actually is within the broader landscape of competitive corporate technology announcements. Most companies operating in fiercely competitive, high-stakes technology sectors have strong incentives to present their achievements in the most favorable possible light, and considerably weaker incentives to actively invite outside researchers to poke holes in those same